what I want to go through now is a few examples that are actually quite important, because the first thing you're going to ask, now that we can fit the metalogs to data, well, how would it be if you fit a metalog to data from some known distributions? How well could it approximate those distributions? Because I've said the metalog can represent most anything. Well, why would I believe that, right? Or why would you believe that? Well, let's try fitting a metalog to some known distributions. So this is 105 points. All these points here, 105 points that I just took from a standard normal distribution. So these are points from the cumulative. Now, the metalog knows nothing about the equation of the normal distribution. It has its own equation, but I can feed in these points and use ordinary least squares to fit a metalog to those points. So what does it look like with various numbers of terms? If I use a two-term metalog, I've got a logistic distribution, which is an approximation of the normal distribution. And it's an okay approximation, not great. What about a four-term metalog? Even with four terms, you're getting very, very close to the normal distribution exactly. 6, 8, 10. By the time we get to 10 terms, it's virtually impossible to distinguish between the normal distribution and the metalog representation of it. Now let's look at how that looks as a density function. Here's the probability density function. Here's the two-term metalog approximation of that density function. Again, I'm just parameterizing the metalog by these 105 points on the left. There's the four-term, 6, 8, 10. By the time I get to 10 terms, the metalog approximation is so identical to the normal distribution, you actually can hardly tell the difference. And if you look at measures of distribution fit and whatnot, I mean, this is way, way out there in terms of, you know, the KS, the maximum difference in probability is so minuscule that you hardly even care for any practical purpose. What about other distributions? That's a normal distribution. Here's a log normal distribution. What if we use a log metalog and parameterize it with 105 points off a log normal distribution and take the same lower bound as 0 for your log metalog? That's the two-term, 4, 6, 8, 10. By the time you get to 10 terms, you can't tell the difference between the log normal and the log metalog. Let's take something else. Here's a very odd distribution. This is one of these U-shaped beta distributions that happens if both alpha and beta are less than 1 when you parameterize the beta. Well, you'd think, well, okay, so we'll use the logit, the bounded metalog with 105 points parameterized by this and with lower bound 0 and upper bound 1. How does it do with two terms? There it is. Awful darn close. 4, 6, 8, 10. Once again, by the time you get to 10 terms, you can't tell the difference. So here's a distribution that is an extreme value distribution. The best fit Pearson distribution, by the way, this is extreme value distribution is not a Pearson distribution. The best fit of all the Pearson distributions is the red line there. How does the metalog fit it? Well, with two terms, 4, 6, 8, 10. Once again, it sits on top of it almost exactly, and it's a much better fit than the best fit Pearson distribution. Pearson distribution can match up to 4 moments. The metalog distribution can match any number of moments corresponding to the number of terms. So it turns out, and we just learned this within the last year, that the metalog distributions are actually infinitely flexible, or maybe it'd be more accurate to say they have unlimited flexibility in the sense they can take on any shape. We didn't know this at the time of the publication of the 26th paper, but now we do. And so this is a new theorem within the last year. Any probability distribution with a continuous quantile function, that is a continuous CDF, can be arbitrarily closely approximated by a metalog. Wow, you can have any distribution at all, anything. It's like a Taylor series, it converges to it. How do we know this? Some of you may remember from mathematics, and this is not something everybody would have learned, but any continuous function can be approximated arbitrarily closely by a polynomial. And there's a theorem called the Weierstrass approximation theorem, certainly not my invention, that shows that this is true. Well, the metalog contains a polynomial. So if you set the non-polynomial terms to 0, now you've got a polynomial. And so therefore, there's a metalog representation that's arbitrarily close. So there's a bunch of observations. A single set of metalog equations can represent virtually any distribution. Now there are these potentially obsolete questions. What probability distribution is best for this application? How do we fit it to our data? Well, we've got an easy way to fit it, and we don't have to ask this question anymore, because no matter what it is, you could use a Metalog for it. There is a practical limitation, and I will talk about these, but they're distributions with spikes, discontinuities, or extremely fat tails. I mean, there's some things you can't do very well, but almost everything you can.